I guess that we can start if you are ready. You should have these packages installed on your laptop to do the hands-on exercises. And all materials are on GitHub. You can download them from this link. I don't know what are the rules here. We should start on time or wait for a few minutes. Many people are there, so maybe we'll just start. So, my name is Przemysław, and this is a workshop about DALEX package. So, if you are not in the right workshop, you can still find your. There are two things on this slide that are maybe important. One is the book on the left by Hasti, Tibshirani, and Friedman about elements of statistical learning. I believe that for many of us, like statisticians, it is the book about machine learning. So I'm using this book for my lectures, but it's quite complicated. We can do something, but students don't understand what is inside. So I think it would be nice to have the book with DALEX. It's a creature that is calling explain very often, and we'll try to explain advanced stuffs that are in the book. Maybe not through math that is there, but from the other interfaces that we can use. I will show you what does it mean. This link is on the whiteboard, so just in case you need it, it's there. We'll spend 3 hours together, so I will introduce myself a bit, just for a few minutes. I'm working in Warsaw, Poland, Europe, so far from here. I'm teaching and doing research in machine learning. Recently, I'm most interested in explanations of black box models. I will tell you what does it mean, black box, and why do we need explanations in a second. Primarily, my interests come from molecular biology. I was working with physicians a lot, doing some predictive models for them. And then I saw that for them, okay, they have models, they trust me that models are okay, but then don't trust the model itself. So explanations are useful for me because I can explain my models to my colleagues. And also I'm interested, of course, in data visualization because all these things are related with visualization, model visualization, data visualization, something. And if you are going to contact me, you can just type Biecek in Google and probably the first link will be about me, and it's easy. There may be some rules that I should say about. First is that feel free to interrupt me if anything is not clear. I don't know whether you are more in the math, from a math background or computer science background or maybe applications. So some things might be harder for someone. Please interrupt me. We have 3 or 4 colleagues here that are eager to help us. Maybe you can wave your hand. Yeah, they are all in the last row for some reason. Yeah, so. If some help is needed, they will help us as well. We'll have a coffee break in 90 minutes. Before the coffee break, we'll have like 2 sessions for hands-on experience. They will be like 15 minutes long each. And then we'll have 2 more sessions after the coffee break. So it should be like 30 minutes of talking, 15 minutes of hands-on experience, and so on. The first part might be a bit longer. Then I have some DALEX stickers, and they will be here, so feel free to collect them if you are obsessed about stickers. And of course, this is a kind of very fresh field. If you have some ideas what you would like to be explained from a black box model, let me know. We have some PhD students that can implement these things, so just let me know what can be added. Okay. So I will start with a short introduction, motivation. Why do we need explanations? Because we'll be talking about explanations a lot, so why do we need them? And I will show you 2 papers that I found very interesting. They are from this year. First is about a research. People claim that they can do a photo of your retina and then predict a lot of interesting factors based on this photo. Factors like smoking status, age, gender, things like that. And all these factors are related with serious diseases like heart attack and things like that. So actually, taking your picture of your retina, they can create some risk score, how risky you are to have a heart attack. Nice applications. Yeah, you can go and take picture of people and scoring them. So other very interesting application of machine learning is presented in this paper. You can use a very simple, very cheap blood test and then predict some various diseases that can be kind of expected based on your results from your blood test. Also, they present some interesting results. So we are reading papers like that more and more often because there is a lot of them in current literature. Machine learning is a very popular domain. But then the question for me is like, imagine that these predictions are for you. Like, this is a scores for you. Would you trust them? Is it really about nice application, shiny tool, or it's about things that we, as a machine learning experts, do we trust these results? Because I would not. Without anything deeper, just based on accuracy, it's not enough for me to to say that, okay, I'm kind of convinced that I will have a heart attack in 12 months or something. So we need some additional tools to extract some information from models rather than just accuracy. So black models, maybe what we are talking about. This is kind of vague term, but 3 things that are commonly associated with black models. These are complex structure. So some models are very complex because there is ensembles of trees or other models. So they have like thousands of parameters, of millions of parameters. So these are complex because of their structure. And also, one may think about black model as a model that maybe is easy or maybe it's very straightforward when we are talking about structure, like a linear model, but the input space is very large. We have like thousands of variables, or in methylation studies, we can have millions of variables, and they kind of influence the final result. So the model itself, maybe it's easy to write the math behind the model, but it's complex in a sense that we don't understand what is happening inside, because there is so many important features, or so many features in the model that might be important. And the last sign that some model might be a black model for us is that variables do not influence the result as in an additive manner, but they working in kind of interaction. So maybe we have just 20 variables, but number of interactions between them is very large. All these things makes the model complicated. It will be hard to explain anyone what does it mean that result is 0.5. So we have a lot of black models like that. We should not be afraid of these models because they are known to be very elastic. They are known to be very effective, but we just need additional tools to understand them better. Okay, and what we can do with this understanding, there are a few things. One is domain validation. So, results like the one that I've presented you, accuracy 0.9999, may be biased, and we may be not aware about this bias, like people were doing a lot of invalid, not valid validations, and the results is simply wrong. Maybe we can extract some new knowledge from the model itself. Maybe it's all about trust, or maybe it's about law. So in Europe, we have the GDPR law, which force some entities to explain their results. Maybe I will talk a bit more about this law thing. So there is even a Wikipedia webpage, right to explanation, and it's about a civic rights to ask why you get a given score. So if some agency gives you a score, so you may think, okay, I would like to know why it's given this way. So it's one of our rights, it should be. And actually there are some papers that discuss this right to explanation, so you can find them and read them or scan them. There is a lot of them nowadays. So I hope you are convinced that we really need these explainers. I have one more reason. There is a very good book, probably most of you have heard about it or have read it, Weapons of Math Destruction by Katie O'Neill. She has a blog, MathBabe, and she was doing some TED Talks, so it's easy to find some materials about her and her ideas. Basically, I've just taken some notes from an interview with her, and they talk a lot. Like, we don't see a lot of skepticism. The algorithms are like shiny new tools that we cannot resist using. So because there is math behind, we trust them, but maybe it's not enough to trust in the math. Maybe we should really know what the math is doing in the model. So what she originally was saying, the era of blind faith in the big data must end. But I think that we can replace big data with a machine learning and it will be valid. It will be, her arguments will be still valid. Lots of reason. So yeah, because of them, there are some packages. Some are in Python, some are in R. I am going to present one of them created in R. And these packages are targeted to answer some questions about models. There are many different questions that you can post, and none of this package addressing all questions, but yeah, questions that are addressed by the DALEX package are how good is the model, how it's working, which variables are important in the model, how these variables address the problem that we have in mind. So actually DALEX is kind of interface to other packages, and there is a larger list of these other packages in this slide. The ones that are bold, these are packages that I am going to talk about, but there is a lot of them, but there's a lot of packages that I'm not going to mention. But they are still very important. Probably some other people will mention them during their talks or something. Okay, so the last slide about introduction is that the DALEX is quite young. Actually, the first commit was in February 18, so it's very, very young. But the research beyond the DALEX is much older. This is just a glue, an interface to many different tools that we can use. And you can think about it as an interface. So there are a lot of methods that are very useful. I am going to talk about these methods. But also we need kind of unified interface that helps us to think about exploration of models, because it's not like just a collection of different tools. We are looking for some unified grammar for the exploration. So this is an attempt to actually create a grammar like that. So you think about DALEX as an interface, and actually there are some dependencies, and dependencies are taking care about the real stuff that is done by the PDP package or aleplot package or other packages. We started something called DALEX Invasion a few months ago. So every month, on average, we have a talk or workshop about DALEX. I and my students, PhD students. So yeah, this is our last talk from this list. We are eager to go somewhere and talk about this if you think it's important. Okay, so model specific or model agnostic. All explainers that I'm going to show you are model agnostic, and what does it mean? So to show what does it mean to be model agnostic, maybe I will start with something that is model specific. So 2 years ago, together with my student Aleksandra Połuszyńska, we have prepared a random forest explainer package, and it was a package that was targeted for random forest models. So you can take a random forest model, and these are large number of trees, so you can extract some useful information from these trees. You can look for some additive effects, you can look for some interactions, you can look for depth of variables in the trees, how often a variable is in a node, where are splits happening for the model, things like that. But this is the whole package about only random forest. And then, of course, people are using other models. There are stacking models, they're doing many different things with models. So we have some tools that are model specific, that are working for linear models only, or random forest model only, or XGBoost model only, or neural networks only. But actually, what I think is more interesting is to look for tools that are model agnostic. So you have just a black box without any knowledge about its structure, and you can extract some information from this black box. And tools like that are very useful if you are the creator of a model, because you have created a random forest, and now you can explore its structure. But I guess in the future we'll be more consumers of models, so someone created a model, maybe sell it to us, or we got this for some reason. And so maybe we are not even able to explore its structure. So we need some tools that are working without structure. So all models I'm going to show you are model agnostic. We are not going to tackle the model structure. It may be even no structure, maybe just a random number generator, who knows. We'll have just interface that allows us to do some exploration. Okay, use case. So to present key features of a DALEX package, I am going to use a data set related to apartment prices. So let me just introduce the data set. It's a fake data set. I have created the data set to show some problems. So don't use it for real purposes, for scoring prices in Warsaw. We have just few columns, price for square meter in the first column, and then there are 4 other columns that we are going to use for model building and model exploration. 4 of them are continuous, more or less. Construction year is more continuous, surface is more continuous. Number of rooms is maybe not that continuous, but still a numeric one. And district is a categorical variable. Yeah, so we can do something with a model. And of course, usually when you think about workflow in machine learning, it's like, let's create a model and then let's use the model for prediction. So there are 2 steps. Of course, they are long and they have a lot of sub-steps, but these are kind of milestones. Yeah, we have some knowledge about the domain, we have some data, so we are building a model, and then having a model, we can create prediction. And there is a lot of good tools to do this step A and B. What we will be talking today is actually about steps C and D. So having a model, we can now ask ourselves, okay, so how the model is working? Can we do something to create a better model? So this is step C. Take model, do something, and maybe increase our knowledge or ask for new data. And step D is about, okay, we have a prediction, so maybe now we can understand which factors are key for this prediction. So maybe we can use some knowledge about the prediction to improve a model itself, to improve our understanding of a model. So these are these steps C and D, which we'll be focused on. So I'm kind of assuming that you know how to do A and B, so I will talk about C and D. So A and B. Let's have a data. Let's take a data and let's create 2 models and let's see what we can do with the models. I am going to use 2 models here. One is a linear model because I guess it's taught on statistics 101 or something like that. So I assume that people are aware of the model. So I am just creating a model which is using these 4 variables in additive fashion to predict price for square meter. And then I am doing the same for random forest model. So, without any deep exploration of the data, just 2 basic models, a random forest and linear model. This is, for me, interesting 2 models because linear models are believed to be easy to explain. So there are these white box models, while random forest is more elastic, but also, hundreds of trees, so maybe it's not that easy to explain what is happening there. So we have these 2 models, and of course, what you would do, you would ask yourself or someone, how good are these models? So maybe let's validate them. So I have additional data set. It's called apartment test with 9,000 new observations, and we can use this data set to actually assess accuracy of a model. And here I'm using the root mean square, but it happens that for both models the root mean square is quite similar. So the fit is like 283 dot something. So we have 2 models, very different one. One is linear, one is very elastic, with very similar performance. And one question is which of them I should use. Second question is, maybe it means that I can create a third model which will take some strengths from these 2 and it will be even better. So what do you think? Which model I should use? Linear one or random forest? It depends. Very good answer. On what? Like, what do you? Okay. Interesting. Yeah. We'll see. Actually, so reason that I've heard about this is that it's better to use linear model because it's easy to implement. If you have to score something in database, there are just 5 coefficients or something, so it's much easier to actually apply this model somewhere. But other people are saying that random forest is more robust or more elastic. So for me, it's not clear from here. We have 2 models with similar performance. Let's see what they are doing. Which one is better? Okay, so actually the agenda for today's workshop is to talk about many different tools to explain black box models, and these tools will be applied to these two models, linear model and random forest model. So then we'll gain some additional knowledge about these two models based on these explainers. So this is a kind of roadmap. There are just less than 3 questions that need to be asked to choose the right explainer. We'll go one by one, cover the explainers for global explanations in the first part of the tutorial, and then the second part of the tutorial will be more related to the explanations of single predictions. So yeah, many different tools. These tools, there are 3. Each tool is kind of, there is some math behind. There are some data numeric tables behind. But for me, it's much easier to focus on plots because we don't have that much time. And I think that plots are useful to have a quick grasp what is getting there. So I will be focused on plots, but keep in mind that behind every plot there is some table, and behind every table there is some method that is used to calculate these numbers. And the last slide is about further documentation where you can find these tables and these formulas. So let's go one by one on these explainers. I said that DALEX is kind of glue language that helps you to operate, work with these explainers in an easy to remember fashion. Every explainer will be created in like 3 steps. First step is to create a wrapper around your model. Second step will be to create an explainer, and third step will be to plot the explainer. So A stands for the wrapper. Black boxes might be very different in input space, very different in results. So what we need to do, we need to kind of enrich black box model with additional data that allows us to operate on the model. So we need to specify a predict function. We need to describe somehow the structure of the data. And I will show you in a second how to do this. Then, so this is the first step, wrap a model. Then we need to create explainer. Explainer is a function that is targeted to explain a particular feature of a model. So average response to continuous variable, average response to categorical variable, things like that. So we have a single question in mind, and then explainer is supposed to answer the single question. And then the last row, plot explainer, is about the interface. Here it will be a visual interface, how we can visualize and present the answer. Whether it's better to present the answer in a tabular form or maybe as a figure chart, we'll see. So these 3 steps. So since we are all talking, we are all using R, so it's easier for me even to present these 3 steps in R code. So here we have just 3 instructions. First instruction is using explain function from the DALEX package to create an explainer. There are some arguments. I will talk about these arguments in a second. So this is something that needs to be done once for a model. We are creating some wrapper around a model. Then for every question that we may have about the model, we need to create explainer. Explainer explains some particular feature of a model. So the second line, single variable, explains how a single variable affects the model response, additional line. And then we have this last part, last step, in which we want to present the answer. Like we are having this question, let's present the answer in a visual form. So we are using a plot function. We can also use a print function to present some tabular data or some other way to represent the answer. So these 3 steps. The first step will be done once for a model. Second step will be done once for a question. And first step will be done if needed. Okay, so why do we need a wrapper? As I said, there is a lot of different ways to create a machine learning model in R. There are 2 very good frameworks. One is Caret, thanks to Kun, thank you. We have MLR also, very recent framework, which gains a lot of interest. There are also a lot of different tools that are not related with these frameworks, but can be used to create a new model, like random forest package, E1071 package, There is a lot of packages that can be used, a neural network package and things like that. These packages have different ways to create a model, different ways to generate predictions. So we need to have some uniform approach to explore these models, and the explain function is creating such a wrapper around these models. So in many cases, it's enough just to put your model as a first argument, and everything else will be extracted. But if needed, you can specify the validation data as a second and third argument. So for some explainers, you need to know the true labels, and you can specify them as a Y argument. For some data, you need to specify a data frame as a second argument, so sometimes they are needed. And if model is using the predict interface, then you don't need to specify anything else. But for some models, you need to also specify some predict function. For example, in random forest, by default, the response from the predict function is a label instead of score. Here, we assume that the predict function returns a continuous, some numeric values. So the predict function will be a wrapper around the random forest predict function to extract the numeric values, votes from trees, rather than labels. All models, all explainers will work for classification and regression. Now we are working for survival models as well. So for regression, it's easier because you are mostly interested in Y. For classification, is sometimes a bit more complicated because you would like to transform the scores to some other domain. So you can also specify a link function. So the link function will convert results from predict function to domain that is meaningful for you. Also, the last argument is the name of a model. As I will show you in a second, what we are going to do, we are going to use explainers to compare many different models. So to be able to do this, we need to have names for these models. So you can, by default, label will be a class of a model. But if you are going to compare a lot of linear models or a lot of random forest models, I want to add a label for these models. So it's a last argument. Okay, so let's do some examples. It will be easier for sure. I will start with examples for global explanations, for the whole model explanations, and the most known is for continuous variables. So I will start with these. I hope that you remember about our use case. It's about a prediction of price of square meter for some apartment. So we have created two models. And what we can do now, we can create a plot like that. On the y-axis, you will have the predicted price for a given apartment, while on the x-axis, you have a single variable. Here it's construction year. Yep, so we have data from different construction years, different predictions, how to understand what the model is doing. So the most known explainer is called PDP, partial dependency plots, and it's working like that. So you can imagine that now for every apartment, we are creating kind of artificial predictions. So we are asking ourselves what would happen if the given apartment will have slightly different construction year, maybe 2 years older or 2 years. Yeah, you can shift these values. So now from each point, you have a curve of possible predictions after altering the single variable. So you have lots of predictions, and since the random forest is not an additive model, so you see that these curves are not parallel. The one on top, they are more flat, while the one on bottom, they are more curved. We see that there is some nonlinear relation happening there. So to summarize the global structure of a model, what people are doing, they are averaging all these curves. So here we have a particular predictions for every apartment, how its price will change if the apartment will be slightly older. What we can do, we can now take average across all these curves and say that in general, the relation between construction year and the output is like that. So these profiles are called individual conditional expectations. IC, there is package, it's a plot for plotting these curves. And the average itself is called partial dependence plots or partial dependence. It's average across all these curves. Yeah, so the story that I've told you might be easily summarized with some math. So we have some expected value for given x, and so we have some estimates for this value. I will leave this math on slides. You have access to these slides. I am rather going to focus on plots because I think it's easier to understand them. So we know how the plot is being calculated. So now we can ask ourselves how to create it in R with DALEX package. So we need to use a single variable function which creates explainer for a single variable. This explainer here has 3 arguments. First argument is the wrapper around the model. So in every explainer, the first argument will be a wrapper. So we assume that we have a black box model. We have created this wrapper, a unified interface to the model. And every time I am going to use some explainer, the wrapper will be the first argument. Then for this explainer, I need to specify which variable is a variable of interest for me. So here will be construction year. And then the last argument, it's by default PDP, but I can put it explicitly. So I can specify how to calculate this explainer. And more or less, all explainers will be working this way. So yeah, you see that the average link between construction year and random forest is nonlinear. Actually, very old apartments are more expensive, very new ones are more expensive, and the middle ones are not that expensive. There is a reason for that in Poland. Like, apartments previous to the Second World War, they are located in nicer places. They are old and, more desired. The new apartments are usually of better quality, at least in Warsaw. So there is a reason why to explain this nonlinear relation. And then this relation is extracted from the data, extracted from the model. And it makes sense. It's not that by accident, it's some fluctuations. Actually, we should expect something like that. Afterward, Second World War, companies were creating a lot of apartments, but they were very cheap and not that high quality. So this is why the prices are lower. Okay, so a nice thing about this unified approach to model explanation is that you can compare many models. And then you can learn even more about your problem from many different eyes. So here what I am doing, I am create a similar explainer for additional model. Now for a linear model, you may remember that the explainer underscore LM is a wrapper around linear model. Other arguments are the same, so explanations for the same variable with the same type of explanations. And now I can use plot function to plot both explainers. The plot function can take any number of explainers and it will plot all explainers in a single coordinates, in a single chart. And now we can see how model responds, how different models respond for a single variable. From linear model, we expect that the response will be linear, that is the name of the model, without any prior feature engineering. And it's like that. Linear model doesn't see the relation because it's not linear, and it is an artificial data set created in a way actually to make the conditional, the marginal effect equal to 0. So we see that there is something that random forest model learned. It learned this nonlinear relation, while the linear model cannot learn it because it is focusing on linear relations. So now I can repeat my question, which model would you choose? Linear model or random forest model? What do you think now? They have equal performance. It looks like they are different in a way how they are capturing this variable. What do you think? Which is better? I think that you are afraid what will happen. So it depends. Okay. Yeah. Yeah. So yeah. So clearly from this figure, it looks like random forest is better for construction year, but since both models have similar performance, so it means that there is some other variable for which random forest is not that good. Yeah. And actually, it will be one of our exercises to see what is the relation between surface and this way hat. Because for surface, the true relation is linear, and linear model is better in handling linear relations. And for random forest, you will see that it's biased. So the trade-off. One model is seeing something, one other model is seeing something else. Yeah, but here we see that there is some relation, or we may believe that there is some relation, and random forest is handling the relation, and this plot is helping us to actually see that there is something there. Yep. The slope here, yes. Yeah. Intercept, no. For some reasons, the reason why intercept is different is that the intercept itself in the linear model is not that interesting for us, because here construction year, the intercept might be like minus 3000 plus 0.5 times construction year. So for construction year, the baseline 0 is not that meaningful. The actual baseline would be the average from construction years. So we need to do something with intercept, but the slope is the same. Yeah. Yeah.
So, a question, why would we get a response versus predictor from model perspective? Why aren't we looking at the real relationship first?
Because, yeah. Very good question. Very good question. So I guess that the data exploration starts with the relation between the variable x and the true y, the true label. And now I can split myself and have two answers for your question. One answer is that here on this workshop we are focused on exploration of black box models. So we are focusing on tools that can tell us what the black models see. So we are not interested in the truth. The truth may be different. We are just interested in what is handled by the black box model. So this is our perspective right now. We have a model, and we are going to learn what the black model is doing, not what the truth is. So this is one answer. The second answer would be that we can use these very elastic models like random forest, XGBoost, neural networks as a surrogate models. So we believe that these models will better handle some relations. They will reduce noise, and then it will be easier to see such relations from things that are learned by these models. Because here, if you have y as a true, on y-axis, if you have the true y instead of y hat, it might happen that just averaging or doing some smoothing, you won't see this relation. The relation is visible when all other important variables are being handled. So we need this model to get rid of all other important variables, to get rid of surface, to get rid of number of rooms, to get rid of district, and then having all other factors handled, then you can see the relation between this variable and the y. So yeah, from one perspective, we are not interested in truth. We are interested in the things that the black box model is actually doing. It would be enough to say that, but the truth is that we can also use these very elastic models to better understand what is the link between the y and the x, better because we are also handling all other x's. So in genomics, it's common that you have like 200 variables, and seeing the relation between a single variable and the y don't tell you anything because the noise is very, very large. So you need to kind of take out all these 999 other variables to being able to see the partial dependence between the one x and the y. Yeah. So two answers. Yeah. Very good question. Actually, in the paper that is introducing LA plots and PD plots, they are discussing interactions. We are not doing this right now because we believe that we don't have enough good enough methodology to actually identify these interactions. So I will talk more about interactions later when I will focus on a single variable responses. It's very important because we kind of believe that if the truth is additive, then it will be enough to use GAM models or additive models to handle the truth. So it might be something not additive there. Yeah, but I don't think that we are there yet to actually detect something that will be the true interaction. So I will talk more about this in an hour or something. Okay. So let me just say that non-serial bullet, it means that actually it seems a very straightforward approach to do this. It makes sense, but people are also showing that in some cases it's not a good approach. And so there is a very nice paper, actually it's a vignette for aleplot package, that shows that if you have axes correlated, the PDP plots is not the thing that you would like to have, because you might have two variables like surface and number of rooms that are very, very highly correlated. And now, in these profiles, you're kind of asking, if you have surface on the x-axis, you will be asking yourself, what would be the model response for apartments, this apartment with surface equal to 100? But you kind of expect that other variables will change with surface as well, like number of rooms. So there are other approaches to these continuous variables called aleplot that are taking care somehow the correlation structure between variables, and they are doing this averaging in a better way, taking into account the distances between different points. So I'm not talking more about these explainers. There is a lot of different extensions. You can follow the paper there. I can just say that actually it will be enough to specify type equal to ale to have these other explainers. Yeah, so there are different ways to create profiles like that. You can be more focused about different, features that are important. So yeah, it will be just enough to change the type argument in this variable. Okay, you can find more in these three papers. The last one discusses the problem with interactions. The second one discusses the problem with correlation between predictors. Okay, before hands-on session, I would like to show you one model explainer. This one will be very similar in structure, but different in terms, like now we are going to handle categorical variable instead of continuous one. So PDP plots are designed, are commonly used, but they are working for continuous variables. You need to have some continuous space to show the relation. So what to do with categorical variables? And there is a tool, it's called factor merger, that was originally created for one-way ANOVA, but now we realize that we can use this tool for similar purposes here. So the tool is working like that. It gives you explanations like that. If you have a categorical variable like district, here the district has, I think, 9 or 10 different levels. So explainer will show you how these levels are close to each other in terms of average model response. So what you actually are doing, you are creating these fake responses for every possible level of your categorical variable, and then these responses are presented on the right plot as a box plot. Here the box plot looks like box. For some reason, I'm not going to talk more about it, but these are box plots. And now you can see which factors are closer to each other in terms of model response. It would be a very useful plot to actually do some feature engineering, like from this plot, sorry for jumping, but from this plot, what you be expected to do is like, okay, I see that random forest is seeing this relation, linear model is not seeing this relation, so I should do some feature engineering. I should cut this construction here in some intervals, maybe 3 intervals, and then I can use these intervals for the linear model, and it will be much better. Here, what you can do, you can say that, okay, clearly there are 10 levels, but only 3 different values. Again, this is artificial data set, so it was designed to be this way. So we have only the districts in the city center, 3 districts close to city centers, and some districts farther from city center. So this is why they are clustered in that nice way. But again, you may think about some feature engineering to actually create a nicer variable, categorical variable, with only 3 levels. Nicer because then your model will have smaller number of coefficients, so it will be more stable. Again, the math behind is described in a paper below, and in this algorithm, What it's doing a very simple thing. It's looking for two closest districts and trying to merge these two districts and then looking for next districts to merge. On the y-axis, in the dendrogram, there is likelihood. So there is a very nice math behind, but I'm not going to talk about it because we don't have time for this. What I'm going to talk is that you can use this plot, you can generate this plot in the same fashion with the use of single variable function. You just need to specify a different type is equal to factor, or this argument, if left undefined, will be extracted from the data itself. So you actually don't even need to do this. You just need to point that you are interested in the variable district. Again, all explainers are generated in a way that you can compare different models. So here again, I'm going to compare random forest model and linear model. And now you see that for linear model, we have very similar coefficients, very similar responses, but random forest is not able to handle this variable in that nice way. Because what is done by the linear model, for every district, there is some coefficients calculated. For random forest model, we need to have a binary split. And having 10 levels, you need to figure out how to do the split in the best way. And if the split is done not in the root, but on some lower level, you are likely to do some wrong aggregation of these levels. So from these plots, we can also see that random forest is not good with handling categorical variables with many different levels, because it needs to find the optimal split, and it's not easy having a large number of levels. There are other panels that may be used on the right side, like you can have box plots, you can have some QK maps or profile plots, many different things. These things actually are handled by the factor merger package. DALEX is just a wrapper around it. Factor merger package has some nice vignettes, so you can use this vignette to actually see what is happening. You can use this vignette to learn more about the random forest factor merger package. I was talking for many minutes. I think that it would be nice to actually spend some time with the R and with the package itself. So I've prepared relatively easy exercises. So first two should be easy, later we'll see. Let's spend 15 minutes on them. I will give you 10 minutes to do it on your own, and then I will slide to my R and do all these answers on screen, so you can follow my answers as well. The link that was presented in the first slide actually also has all these answers. So if you are lazy, you can just copy them to your R session and see how they are working. We'll have 4 sessions like that. I will be going around, so if you have some questions, please let me know. And we'll go further in like 10 minutes of these things. So let me just go through these solutions on my laptop, and we can go further. Okay. Load data is there. As I said, we need to create a model. Linear model is easy one. Random forest will be easy as well. The only thing with random forest is that it's kind of random. There is a seed rated with it. So to get this equal performance, every time, every new version of random forest, I need to look for seed that is giving the equal performance, because for some seeds we'll have a better results, for some seeds we'll have a worse results. So it's fun itself, but here with seed 3, I'm getting the same performance. So I have 2 models with equal performance. So now I can create an explainer. I specified a model. I can leave it without anything else because the data is being extracted from a model. But here I'm going to use additional data, validation data. So I'm specifying the validation data as additional argument. I'm doing the same for the random forest model, and here I'm creating explainer. Okay. So to have some new plots, I will add a support vector machine model. It's easy to train the model. There is many different ways to train the model, but here I'm going to use E1071 library, and there is a SVM function in this library. It's the same formula, same data set. I'm going to create explainer, and now having all these models, all these wrappers around linear model, random forest model, and SVM model, I can compare these models through explainers. So let me just show you the plot. This is a very, yeah. The validation data has like 9,000 of rows, so it takes some time to calculate these partial dependency plots, because for every observation, right now we are calculating predictions for different construction year. It might be done in a smarter way. We are working on this, but right now it's kind of very slow approach. So here is actually a nice example, because for SVM, with kernels that are being used here, we expect some this quadratures, and for linear models, as you saw, there is no relation. So you have these three models. One is kind of, we know that is bias on edges. Random forest will generate splits, and for splits, it will average out everything that is on the left or right end of a variable. So this is why we are having this small slope on edges. For linear model, we have just line, horizontal line, and for support vector machines, we have these nice curves. And you see that support vector machine is handling much better this nonlinear relation here, because it's not biased. But on the other hand, you may ask yourself, in next years, like 2020, what will happen? Yeah, I'm going to really use this model. Do I believe that it approximates the data the right way? So we can learn a lot from such explainers. By comparing them, we can be more or less eager to use one of them, despite the performance, because the accuracy is calculated on some data set. As I will show you, the accuracy for SVM model is much better here, but again, accuracy is one thing, and yeah, our trust is something else. Maybe it's not that easy to calculate, but yeah, it's there. Okay, similar things you can do with factor merger plots. You will get very similar results, because actually SVM is very similar to linear model when it comes to categorical variables. So other explainers. Before break, I would like to show you other explainers that can be used for general models, for global explanations. One would be an easy question, like how accurate is the model? Again, we had this problem that we have two models with very similar accuracy, but for sure it's not everything that we can say when we're talking about accuracy. Accuracy in many cases is a function of residuals. Residuals is a difference between the actual value and the model prediction. So maybe in addition to average accuracy, we can also plot the whole distribution. And this is something that you can do with the model performance explainer. This function, model performance, creates an explainer around the model. No need for any additional parameter. Model is the only needed parameter, required parameter, or wrapper around the model is the only required parameter. And now we can use the plot function and compare many different models among them. We knew that these two models have equal performance, so the red dots, which stands here for root means squared residuals, are in the same place, but the distributions are very different. For random forest, we see that the distribution is shifted towards the smaller values. So on average, in most cases, it has smaller errors, but sometimes errors are huge. There is small fraction of very large errors. And you can plot the distribution in another way. Instead of box plots, you can use a cumulative distribution plots. Empirical, here is 1 minus empirical cumulative distribution function. So on the y-axis, you have fraction of observations with residuals larger than a given value. So what you see here is that if you are looking for observations with very small residuals, smaller than, let's say, 100, only random forest have residuals like that, linear model mostly have residuals between 100 and 500, but then for 500, all observations, maybe not, all residuals generated with linear model are smaller than 500, but there is a fraction of them, like 10%, for random forest model, which are larger. So it looks like the orange curve is better, despite the fact 10% of residuals that actually are very bad. And we later will see that these 10% are actually very important apartments, so we should be focused on them more. Yeah, but to say this, I want to introduce you a part of a DALEX universe. It's called Auditor. So it's a separate package integrated with DALEX. And what the package is doing similar to plots like that. So I don't know, are you familiar with these plots? These are diagnostic plots for linear models. So if you have a linear model, and if you are using a plot function, plots like that will appear. So there are 6 plots. By default, only 4 of them are being presented, but there are 6 plots that are showing some possible problems with model fit. And there are predicted values against residuals, predicted values against standardized residuals, cuckoo plot for residuals, many different things. So what the Auditor package is doing similar diagnostic plots, but for any model. Why to focus on linear models? Actually, I think that even for models like random forest or others, you should still be able to use diagnostic plots, and some of them are actually valid to use, so yeah, why not? Here is an example of a plot that can be generated. It compares the residuals, so predicted minus truth minus observed, versus the observed value. The left plot is for random forest, the right one is for linear model. So what you see for the random forest is that for cheap apartments with the smallest prices, the fit is pretty good, around 0, but place in which you have the worst fit, the highest residuals, is actually for the most expensive apartments. And you cannot learn this from accuracy itself. You cannot learn this from performance distribution. You can learn this from this plot, that the worst fit is for the most expensive apartments. And now you can ask yourself, is it okay for you? Is it like only accuracy matters, or is it like the most expensive apartments are there in which you are able to generate the largest profit? And if you are targeting your profit from these most expensive apartments, why you are underpredict their prices? Because what you are effectively doing in this random forest model, you have very negative residuals, what means that your predictions are far below the truth. So apartments are more expensive, should be sold, or were priced higher, but your model is actually biased towards the lower prices. So it's not only about accuracy, because here you clearly lose some profit. And you are able to see this from plots like that, diagnostic plots, which compare the truth against the residuals. So there is more about diagnostics that can be done. And it's easy to do this with Auditor package. Auditor package has a function audit, which takes explainer, so this wrapper. The wrapper have everything that is needed. So audit takes the wrapper, and then there are different plot functions. Plot residual is generating plots like you saw before, residuals versus truth, residuals versus particular X variable, and you can use these plots for some future diagnostic of your model. The Auditor package is on CRAN, it's on GitHub. There is some nice vignette, some cheat sheets, so you can quickly learn about different diagnostic plots that can be applied to any model. And again, it's nice that having this unified interface, now you can not only plot diagnostics for a single model, but you can also overlay diagnostics for many different models and decide which model are better if you need to choose one of them. Okay, or one of, not two, maybe you are going to choose one of 10th model for something. Okay, so the last explainer that I'm going to show you before break is about variable importance. I like this one because there's a very simple idea which was, for years, but wasn't exploited until recently. So, yeah, some models like linear models have their built-in methods to guess which variables are more important, like significance or coefficients, standardized coefficients, something like that. Other models like random forest or extreme gradient boosting models, they have also some model-specific ways to handle with variable importance. Recently, the idea is very, very straightforward, but it was published recently in 2018, so this year, this year. Actually, you can use the same concept as was introduced for the random forest to generate a model agnostic feature importance measures, and they will be still meaningful. So let me say more about this. Again, math is here, but I am going to describe this idea on a plot. So what we are doing here, we are taking a model. You have the model fitted to your data, and you can calculate its accuracy, its performance. So it's kind of loss function. So now you can ask yourself, what will happen if you destroy a single variable, destroy the relation between a single variable? What we are not going to do, you are not going to refit the model, because it's a black box model, you don't know its structure. Maybe it takes months to create the model because it's heavy, it's very complicated, maybe it requires a very specialized hardware or something. So you are not going to refit the model, but what you can do, you can take a column from your data set and just shuffle values in this column. And then you can see how the performance of a model, the accuracy of a model, will drop after this shuffling of a single variable. So on this plot, you see the performance of initial model, the single interval with just one line on the bottom. The performance was, as maybe you remember, 283. And then if a column number of rooms is shuffled, then the performance calculated on this changed data set will be lower. Will be lower because, of course, if the number of rooms was important variable, so now you have destroyed this relation, so it should be lower. And you see how much it will change. So it will drop even further to like 400. The most important variable here is district. So if you shuffle districts, the column district, performance of a model will drop from this 280 to like 900 or something. Or, yeah, 900 something. The baseline is actually information how much the performance will drop if you shuffle all variables. So it's the most extreme case. Model is not seeing anything. It's the worst fit because we are operating on the random data. Of course, model is doing some predictions. So between the baseline and the full model is a space which you can kind of fill in by different variables, and you can compare importance of different variables by the amount of loss function that will be increased when the given variable is shuffled. So in many cases, if plots like that are being presented, they start from 0. So 0 is the baseline for bar plots in most cases, and then length of the bar is related with the importance of variable. Here, we are not doing this because if you are going to compare two models, actually it's very good to know not only the importance of a single variable, but also the initial importance of a model. In this case, these two models were very similar in terms of performance. In exercises, we will see that it's not always the case, but yeah, we can compare how good was model with this variable and how good is the model without this variable. Not only between variables in a given model, but also between models itself. Okay, so here we have importance measures for two models. And could you find some differences between these plots? Is there a variable that is behaving differently in a linear model and a random forest model? Which one? number of rooms is 1, like in random forest it looks like very important one, while for linear model it's not that important, probably because it's correlated with surface, and surface just takes all the importance that is attributed with both correlated variables. And second, which we should expect that will be different, is the construction year, which clearly is not important for linear model, and we saw that there was no importance, and it is consumed by random forest and is related with some drop in performance of random forest if it's removed. So you can compare models with plots like that, and then you can learn which variables are being handled by one model are not being handled by another model, and maybe sometimes it will mean that, okay, it's a relation that can be grasped by random forest, like construction year, and cannot be grasped by a linear model. Or maybe it's related with some correlation between features. So just by seeing what is being seen by random forest and what is being seen by a linear model, you can learn something about these two models as well. Yeah. Yeah. So again, we have like 15 minutes, 13 minutes to coffee break. Let's use this time to practice with these two explainers. Again, I am asking you to use the model created in the previous example, previous exercise. But now let's see what we can do with model performance function and with the variable importance function. Having three models, it will be even nicer to see what are the differences between these three models. One is very elastic, but robust on ends, like random forest. One is not, like support vector machine, and one is very stable, like linear model. So these three models will be very nice to compare. And again, let's spend 10 minutes, and then I will show you my results for this exercise. Also, if you have some questions related to math, you can use these 10 minutes to ask me. And, yeah. So let me show you my answers to these questions. So first was about model performance. What I should mention, and I will do this right now, is that every explainer actually creates a data frame with information needed to do something. So in all cases, the data frame has a last column with name label, which is the label of name of the model, because it is designed in a way that maybe you can join many different models with same structure. So it's kind of tidy approach to model explanations. And here what we have is the predicted value, observed value, the difference in the label. But for every explainer, we have overloaded a plot function and a print function. The print function is overloaded in a way that it presents quantiles, 11 different quantiles from the distribution of residuals, and the plot function is overloaded in a way that plots the distribution either through empirical distribution function or through box plots. So you can have this for many models, and then you can compare different models. Here we have three models. It's easier for me to read something from the empirical distribution curve. Some people are asking me why it starts from 1, not from 0. For some reason, for me, it's much easier to think about curves that are being smaller. But yeah, you can, of course, revert this. Every plot generated with the plot function is actually a ggplot plot. So you can apply all these coordinates, other modifiers to the ggplot plot, and you can reverse the y scale as well. So here we see that the support vector model is better in terms that all residuals actually are below the residuals for random forest and linear model. So we may have a high expectations because it looks like it's a very good model. Also, from box plot, it looks like, to make it easier to compare, I need to squash it. the initial loss was much better, almost 2 times better. Still, there are some apartments with large residuals, but there is a small fraction of them. It's much better in terms of these heavy biased predictions than in terms of than random forest. So model diagnostic can be done with auditor package, and there are different plots that can be created. I will just go through them. Of course, diagnostic is something that is very important, but in many cases omitted. So I guess that nowadays we are so focused on training models, but there are many things that are important in both preparation for training, so model diagnostic, and also understanding of a trained model. So we are kind of biased. So diagnostic is something that can be done with the auditor package. Here it looks like Creeper. I don't know if you have kids that are playing in Minecraft, so you can show it to them, so they will know what it is. And model importance, I will show you the plot for model importance because maybe there are some things that should be repeated, judging on the questions that I've got. One is that here the importance of variable is judged based on shuffling a column in the validation dataset, and we are checking how much the observed accuracy dropped. What we are not doing here, we are not refitting a model without this variable, and there are some reasons for that. One reason is that in theory, after removing a single variable, you should do the whole model preparation thing with care. So you need to look for correlations. It's not like just drop one column and do everything in the same way. Maybe the column was important, maybe it was correlated with something. You need to do some smart modeling without the single column. Also, maybe to fit a model, maybe you need a lot of specialized hardware or software, some external libraries. Maybe you need a large cluster with lots of RAM, and you are not having these resources on your laptop. So there are many different reasons why you might not be able to refit a model. So we are not doing this. We are just checking how the model performance is dropping if given variable is changed, altered. And here the easiest way to actually alter a variable is by shuffling, because we are keeping the same distribution of values, just changing its order. So it's kind of, from my perspective, it's okay to do this. And here there are 3 models. They are nice because they have different initial performance. The SVM model starts with much better loss function. And even if you use the model with FVM, and if you don't really able to kind of estimate number of rooms or ask for number of rooms, maybe you have a model, you kind of bought a model, but now you cannot use the model because you don't have, in your data, you don't have this column, but still, even putting here some fake numbers, you still have better performance than these models trained on all variables. So you are not only able to compare variables between, within a model, you are also able to compare models with or without some variables between different modeling approaches. Yeah? So here, construction year, if you break the construction year, actually you will be worse than linear model with the construction year because it's not using the construction year. This measure, this loss, is something that you can compare across different models. And it's also, I think, very useful because I guess in the future we'll have like, physicians, and they will have a shelf with different models, and they will have like, 10 different predictions. And then they will ask, okay, for these patients, which predictions I should use? And these models will explain, will compare their predictions. Kind of board of models, and these models need to explain themselves or just justify their predictions. So when I think about explaining, it's always across different models. And plots like that helps you to compare different models also. You can, of course, remove start all these intervals from 0 or from 1, and there is some arguments, type equal to row or something like that. But then you will lose this information, how good was the initial performance of the model. Okay, so that's all when it comes to global explanations. The next part of the workshop will be focused on an explanation of a single prediction. So the difference is that here we have the model as a whole structure, the whole model. And after the break, we'll be talking about cases in which you have a single data, some prediction for the data, and then you are going to understand how variables affected the single prediction. So it's kind of different approach, but let's have a coffee first, and then we can talk about this approach.